You've probably heard this sound before. They all sound the same because they use the same system: air brakes. But why have some of the heaviest vehicles in the world trusted the same technology for more than 150 years? The answer is not just engineering. It is a design philosophy built around one simple goal. When something goes wrong, the vehicle must stop. It must never lose its brakes. And that single principle is what turned air brakes into one of the most important safety systems ever created. Let's find out how it works. To understand why trucks use air brakes, we need to go back to the year 1869. And the story begins not with trucks, but with trains. At the time, each rail car had its own brakeman. When an emergency stop was needed, the engineer had to blow a whistle to signal each brakeman to apply the brakes manually. On a train stretching hundreds of feet long, that was a disaster waiting to happen. George Westinghouse, who was only 22 years old at the time, solved the problem with compressed air, allowing braking force to be applied to every rail car almost instantly. His invention completely transformed the American railroad industry. And what many people don't realize is that Westinghouse was also the man who helped bring alternating current electricity to the United States during the famous battle with Edison. A few decades later, as the trucking industry expanded rapidly during the 1920s, engineers faced a similar challenge. How do you safely stop trucks that keep getting heavier and heavier? Hydraulic brakes, which worked well on passenger cars, had one critical weakness. A leak could mean a complete loss of braking power. For a truck weighing tens of thousands of pounds and traveling at highway speeds, that was not a risk anyone could accept. Fortunately, the solution had already existed for nearly 60 years on Westinghouse's trains. Most safety systems follow a familiar logic. They stay inactive under normal conditions and activate only when needed. Air brakes work in exactly the opposite way. Inside the system are extremely powerful springs that are always ready to apply the brakes. When the vehicle is operating normally, compressed air keeps those springs compressed and inactive. If air pressure drops too low for any reason, the springs automatically engage and apply the brakes. The vehicle begins to slow down and stop, even if the driver has no time to react. In other words, when the system stops working, its safety mechanism is only just beginning to work. Hydraulic brakes in passenger cars operate the opposite way. When braking force is needed, hydraulic fluid is pushed through the system. If the fluid leaks out, pressure is lost. And when pressure is lost, braking power can disappear completely. Under heavy and continuous braking, the fluid can even boil, creating air bubbles inside the lines and reducing the system's ability to transmit force. For a truck weighing tens of thousands of pounds, that is simply not an acceptable risk. This design philosophy is known as fail-safe, and it is the foundation of the air brake systems used on trucks, trains, and many other heavy vehicles around the world today. So what exactly is inside an air brake system? Everything starts with the air compressor, which runs continuously and is driven directly by the vehicle's engine. Air is compressed and stored in tanks at pressures of around 90 to 120 psi, several times higher than the pressure inside a typical passenger car tire. These tanks act like backup batteries, storing enough compressed air to perform multiple emergency brake applications even if the compressor suddenly fails on the road. Interestingly, the driver does not directly create the braking force. All they do is open a valve. The real work is done by the compressed air that has already been stored inside the system. The system also includes an air dryer, which removes moisture before the air reaches the storage tanks. This helps prevent ice from forming inside the brake lines during winter and protects metal components from corrosion over time. A pressure governor automatically turns the compressor on and off to maintain a stable air pressure level. The entire system operates almost silently throughout the journey. And every time you hear that familiar pshh sound, you are hearing dozens of components working together to control a machine weighing tens of thousands of pounds. Now, imagine this situation. You're driving down the highway when the truck in front of you suddenly slams on the brakes. At 65 miles per hour, a fully loaded truck weighing 80,000 pounds needs about 300 feet to come to a complete stop. That's roughly the length of an entire football field from end zone to end zone. A passenger car traveling at the same speed? Less than half that distance. The difference is not because truck brakes are weaker. It is because physics does not make exceptions. A heavier object requires more energy to stop, and no braking system can change that. What air brakes do is make sure that every one of those 300 feet remains under control. All 18 wheels receive braking force almost simultaneously from the same system, allowing the truck to slow down in a stable and predictable way. And that is why engineers do not try to defeat physics. They simply try to control it. Their goal is not to make the truck stop in the shortest possible distance. Their goal is to make it stop as safely as possible. There is one thing that makes trucks fundamentally different from passenger cars. Most of them are not a single unit. A tractor and a trailer are two separate vehicles connected together, and they can be disconnected at any time. This creates a challenge that hydraulic brakes cannot solve as neatly. To transmit braking force from the tractor to the trailer using hydraulic fluid, you would need sealed fluid lines, complex couplings, and a bleeding process every time the connection is removed or reattached. With air brakes, the solution is much simpler. The entire connection relies on two air couplings known as glad hands. A driver can connect them in just a few seconds, allowing the tractor and trailer to operate as one integrated system. But the more interesting question is what happens if a trailer suddenly becomes disconnected while moving down the road. In a conventional hydraulic system, losing that connection could mean losing braking force to the trailer entirely, leaving several tons of metal rolling freely down the highway. With air brakes, the opposite happens. If an airline breaks, air pressure is lost. The springs engage automatically, and the trailer applies its own brakes. U.S. federal regulations even build this principle into law. If air pressure drops below 60 psi, the brakes automatically apply without any action from the driver. Air brakes may be a fail-safe system, but fail-safe does not mean maintenance-free. Before hitting the road each day, commercial drivers in the United States are required to perform a brake inspection known as a pre-trip inspection. They check for air leaks, drain any water that has accumulated in the air tanks, and inspect the condition of the brake linings. This is not just a routine formality. A severely worn brake lining can significantly increase stopping distance without the driver even realizing it. Another issue that receives less attention is brake fade. On long mountain grades in places like the Rocky Mountains or the Appalachians, a truck weighing tens of thousands of pounds can convert millions of joules of kinetic energy into heat in just a few minutes. If the driver relies only on the service brakes, excessive heat can cause the friction material to lose effectiveness, reducing braking power even when the same amount of force is applied to the pedal. In extreme cases, the brakes can even catch fire. That is why truck drivers are trained to use engine braking together with air brakes on long downhill stretches. Even so, air brake systems are still easier to service than hydraulic systems in one important way. After replacing a component, there is no need for a complicated bleeding procedure. The system simply needs to be repressurized and checked, allowing the vehicle to return to service much more quickly. In 2025, Aurora officially launched the first commercial self-driving trucking service in the United States. No driver, no one sitting behind the wheel, just sensors, software, and a truck operating on the highway by itself. And underneath all of that technology is still an air brake system. Tesla Semi entered large-scale production in 2026. It is fully electric and designed for the future of freight transportation. But its braking system? It still relies on the foundation of air brakes. This is not a coincidence. Self-driving systems can experience software failures. Sensors can be affected by interference. Network connections can be interrupted. But the steel springs inside a brake chamber do not care about software bugs or lost signals. When everything else fails, the fail-safe mechanism continues to work exactly as designed. That is why engineers are not trying to replace air brakes. Instead, they are adding more electronics and intelligence on top of them while keeping the same proven foundation underneath. Westinghouse invented this system in 1869 for steam trains. More than 150 years later, it is still being used on the newest generation of self-driving trucks. Air brakes are not the kind of invention people usually think about when they talk about technologies that changed the world. Nobody brings them up at dinner. Nobody puts them on inspirational posters. Yet every day, millions of shipments move across America, and millions of people travel safely on highways shared with heavy trucks, thanks in part to a system built around one of the simplest engineering philosophies imaginable. Don't try to be perfect. Make sure that when things go wrong, the consequences remain under control. And perhaps that is the most valuable lesson a truck can teach us.